So the next one we are going to discuss over here is interpretation. So interpretation is assigning the meaning for your propositional logic statement. So we are going to verify whether the given statement is true or false, right? A proposition is given for you and a truth value is given for all the propositions into it. So we are going to identify whether the given propositional logic statement is evaluating to a true or false. So that is called the valuation or interpretation. So we'll see that. Okay. So interpretation is assigning the truth value of your propositional logic statement and verifying it. Okay. So for these kind of interpretation, you should know the base, right? Like we should know what is the valuation for each and every connectives. When the proposition that is given to is a proper proposition, then surely it validate to something. Okay, so I just write it like here for all the interpretation. I'm just going to give the statement for all. Interpretation of true is 1 and interpretation of false condition is 0. Okay, and when can you say a negation? How can we interpret a negation here? Negation X. Negation X will be 1 if your interpretation of X is equal to 0. Okay, else interpretation of negation X is equal to 0. Okay, so you remember your truth table. And similarly, for all the proposition, I just write 1 or 2. You can follow the remaining things. When I say interpretation of X and Y, your X and Y will be 1 if your interpretation of X is equal to 1 and interpretation of Y is equal to 1. Only when X is equal to 1 and Y is equal to 1, your X and Y will be 1. Okay, so else it is going to be interpretation of X and Y will be 0. So similarly, for all the connectives, you have the statement. So just remember this truth table. Okay, I just give 0, 0, 0, 0, 0, 1, 1, 0, 1, 1. Okay, and what will be your negation X? The reverse of it. You'll be having when X is equal to 0, your negation X will be 1. When X is equal to 1, your negation X will be 0. Okay, and the remaining connectives, X conjunction with Y. Okay, X and Y will be only true when both are true. And X or Y, it is true for if either X or Y's interpretation is true, is 1, your resultant will be 1. When both are 0, your result will be 0. And what about your implies condition? Implies condition works like true, sorry. It's in zeros and ones, right? Only for this criteria. Okay, when X is true and Y is false, and X is 1 and Y is 0, your interpretation goes 0 and remaining things it is going to be 1. And bidirectional conditions, when X and Y are same, either it is 0 or it is 1, you'll be getting your resultant as your 1. Others is 0. Okay, so this is about your interpretation. Or you can also call this as evaluating and propositional logic statement. Okay, so when you have a pass tree structure for it, like when I write the statement P implies Q and R, how will you draw a pass tree for it? First, we are going to do it as P, Q, you'll be having implies, and that is then connected with R. Okay, so now when you want to evaluate this pass tree, assign the values for it, like given the statement, propositional logic statement PQR with some values. Let me take P is 1, Q is 0, and R is 1. How can you evaluate the resultant of it? Okay, so always while scanning a pass tree, you have to scan from left to right, combining all the leaf nodes together. So first we'll be doing this operation from left to right. Okay, so you'll be having a reduction here. P implies Q. Okay, P implies Q. So for P implies Q, if this value is 1 and this value is 0. So 1, 0, your resultant for your P implies 1 will be 0. So here this node will be evaluated to 0. Now it is 0 and 1. How does your AND works? AND works when both X interpretation of left side and interpretation of right side should be 1 for getting the resultant to be 1. Here it is 0 and 1, so the result is 0. So totally interpretation of this entire propositional logic statement is false. Okay, so this is how you do it. Okay, and while validating this, see, for any interpretation, there is something called a model. Okay, a model is something that is defined like for any proposition W, we call that as model. For any propositions of W is the proportional value. And if there is an interpretation, interpretation of this W is equal to 1, then this is called a model. Okay, for any set of valuation interpretation for all the given proportional variables of a model. So in this case, I have assigned P as 1, 0, 1. Okay, but here it derives to 0, but we are going to consider some interpretation such that it derives to 1, then this is called a model for a given propositional logic statement. Okay, and you can write it as I interprets W. Okay, so I verifies W, you can call I verifies for this interpretation, your W actually verifies it, or you can also call it as I satisfies W. Okay, so this symbol is important. This symbol actually, we call it as a semantic entitlement. So semantic entitlement actually says that, okay, let me take this as the next one. Okay, so this is called as semantic entitlement. Okay, so semantic entitlement will be combined like this. So just okay, two propositional logic statement can be connected using this semantic entitlement. So the meaning of this semantic entitlement actually means if your LHS derives to true, then surely your RHS should derives to true to make it valid. Okay, so to make this semantic entitlement valid, like we can say something into this propositional logic function like this, it means that for all the interpretation of your LHS that goes to true, your RHS should be true. Okay, so that is your semantic entitlement. So let me take one example to show that how does your semantic entitlement works. I'll take two statements. P and Q semantically entails P R Q. Okay, so it actually means draw the truth table PQ, P and Q, PRQ. So I'm sorry, this is Q. So I'm just writing the truth table, true, 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 false. Either use true or zeros or ones, or everything is going to be the same. False, false. Now the pass tree for truth table structure for P and Q will be true, false, false, false. And for PRQ is true, 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 and it is false. Okay, so now consider the line where your LHS tends to true. What is your left hand side? Left hand side is P and Q. In which place of your truth table you have P and Q to be true? Only in this place. Okay, so here you have P and Q to be true, and for that corresponding interpretation of P and Q, what is the resultant of your RHS? It is also true. So you can say that it semantically entails. Can I do the reverse of it? If I write PRQ, semantically entails P and Q. If I write the statement like this, for all the statements where you have P or Q to be true, this 1, 2, 3 places where I have for certain interpretation of P and Q, my LHS tends to true. I have to check whether your RHS is also true for it. No, see, 2 places it fails. So this is not semantic entitlement, but these statement actually semantically entails. Okay, so this is how your semantic entitlement works. Now we have few definitions. So with this, we can wind up your first altogether session. So here, these terms could be a normal one, like you could have heard of all these things. So when we can say a statement to be valid, a propositional logic statement to be valid. Valid can also be said as tautology. Tautology is a place where for all interpretation of the given statement, if it semantically entails W, then you can say that it is a tautology function. I'll take one example. P and Q implies P. So I'll be having PQ. I derive P and Q, and P and Q implies P. So what is the truth table for it? True, 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 false, false, true, false, false. So what is P and Q? True and false for the remaining criteria. And what is P and Q implies P? So true, true will be true, and false, true will be also true. Okay, so for all the interpretation, for all possible interpretation, if your RHS derives to true, then we call that as a tautology. So when you draw a truth table, if all the entries are true, then that is your valid proposition. Okay, either we call it as valid proposition or we can call it as tautology. Both are going to be same. Okay, so this is the first definition that you want to know. And what is invalid? Invalid proposition is for some interpretation, it doesn't semantically entails. Okay, somewhere you have a false statement. Okay, that is your invalid statement. And what is unsatisfiable? Unsatisfiable is, okay, what is satisfiable first? When you can call a proposition to be satisfied. For some interpretation, if a model exists, okay, for some interpretation, if it derives to true, then that is called a satisfiable one. Okay, see, a valid is one where for all it has to be true. If at least for one interpretation, if it is true, then that is called satisfiable. If one interpretation, if it is false, then it is called invalid. And what will be your unsatisfiable condition? For all interpretation, if there is no model, if it derives to false, that is called unsatisfiable, or you can call as a contradiction function. Okay, all false condition. So these are all the definitions that you want to know before moving to your natural deduction phenomena. Okay, so what all discussed in this first session, Ma? So first session, we have started with what all the alphabets for propositional logic. And we saw how to write a propositional logic statement, what all the connectives, and how to draw a pass tree, define a proper proposition, and how to evaluate it, and how to find a model for it. Okay, so with that, first session winds up, and the next session is all about your natural deduction. Thank you.